Hi, my name is Ian, and I'm a research scientist at the Lower Columbia Estuary Partnership. And this is a quick presentation we threw together about the innovative applications of UAV and wetland monitoring, and specifically an overview of the Blue-UAS and sensors that we have. So overall, we'll discuss the broad UAV applications and monitoring, federal restrictions on the UAV, an overview of the Blue-UAS drone and sensors. Then we'll discuss each of the sensors in order, so LiDAR, multispectral, and thermal, and some imaging applications of each. And we'll conclude with some next steps and topics for discussion at the end. So UAV applications and monitoring. Number one, UAV means uncrewed aerial vehicle. I've been using that a lot, and we'll continue to use it throughout this presentation, so good to define it. So that data has become really vital and critical for the entire region. So it's very useful for project design, construction, monitoring, research of critical uncertainties, and a whole host of other things. UAVs allow for high cost efficiency, making large-scale monitoring and restoration projects viable. So for example, the traditional transect survey is often less than 1% of a site. A UAV can very easily survey the entire site in just a few days. Technological advances in UAVs and remote sensing as a whole allow for a huge amount more data and higher accuracies as well. For example, the rise of satellite data has really benefited remote sensing. But that's outside of the scope. So, federal restrictions on UAV use. Why exactly do we have a new drone? So, rules and regulations implemented by federal agencies made non-USA made drones illegal to fly over federal land. So all permits require the Blue-UAS designation to operate over federal land. So that means the Department of the Interior, Department of Agriculture, Department of Defense. So any federal agency, you must have one of these drones. And then upgrading the drone from the DJI drones to this new Harris drone really increases the quality and the quantity of data we can collect. And this is a list of all of our sites that are on federal lands. So if you look at this, it's mostly Department of Interior with a few Department of Agriculture and Department of Defense lands. So this is our drone, and all of the drones we really have. So the one on the left is our DJI Phantom 4 drone. The one on the right is our DJI Phantom 4 multispectral drone. The one in the back is our Harris drone. We'll talk about in a little bit. So number one, these are restricted by the federal government. Like, we cannot use these over federal land at all. But we highly, highly recommend them because they are plug and play. You don't really customize them. You buy them as a whole, and they're up in the air in 10 minutes. It's pretty fabulous. They have a 28-minute flight time per battery. We have huge numbers of batteries. You have about 1 mile of range with ideal conditions. After that, you can't really see the drone anymore, and it loses signal. The drone itself weighs about 1.3 kilograms, and the entire transportation weight, so drone plus battery plus case, is about 7 kilograms or 14 pounds. The drone itself is about 1 foot wide. We often, in fact, landed on this box down here as our just landing platform in the wetland. So, we'll happily bring this thing into a wetland with us. It's pretty delightful. It has a maximum temperature of about 104 degrees Fahrenheit. We frequently find that we do overheat these drones in the height of summer when it's super sunny. And then, we just have to find some shade and wait a while. So this drone is equipped with a nice RGB sensor and a Centera NIR sensor. This one is equipped with a 5-band multispectral sensor. This drone just has GPS GLONASS. This one has an RTK Ajax and PPK. So that's the little knobby thing on top. So now let's talk about the big drone in the back. This is Hildegard, the Harris Aerial H6 AG Plus electric hexacopter. It's Department of Defense approved, fully customizable. So that means we can slap most any sensor we want to onto it. And it's pretty easy to rewire everything. You can change our ground control station for if we need to. We can, get more batteries. We can throw a generator on it, throw a hydrogen generator on it. We can do a lot of things. Strap a GoPro to it, which we've already done actually, so we can actually see where we're going. We had about a 45-minute flight time per battery. We have 6 batteries. Here's one of the batteries. These boxes are like 50 pounds. It's awful. The entire drone itself weighs about 180 kilograms with all of the stuff, so that's about 400 pounds. We are not bringing this into a wetland with us, and if you have any other option. If we can drive up, we'll do that. If we can throw it on a boat, occasionally we'll do that, but that's really it. It has about an 8-foot diagonal wingspan, so from here to here is 8 feet across the drone. So we need a very large surface area to fly it and land it. It has a maximum temperature of about 120 degrees Fahrenheit, and that's this thing right here on top. This one is the only thing that ever overheats for us. Everything else has stayed very cool, very awesome, and it's never really crashed for us, like shut off or frozen or anything like that. So we have 3 sensors on it right now. So we have a LiDAR sensor right here. We have a multispectral right here. We fly these 2 things together at the same time. We also have a thermal sensor right here. So I want to talk a little bit more about the sensors, but I just want to flash this slide first. Number 1, we have the TrueView 515B LiDAR sensor. So here are some stats about it. I'll talk more about that later. We also have the MicroSense Ultim PT multispectral sensor. Again, we'll talk about more about that later, but it's 5-band multispectral plus thermal plus panchromatic. We also have that Workswell wireless enterprise thermal sensor, which, is a very, very good camera as well. Side note, but in this picture, here's our flex tower, and here's the drone, and here's my car that we drove right up to with. It was pretty great. So the actual process of acquiring drone data. So this is kind of the workflow. So number 1 is the acquisition stage. So that means pre-flight planning, so like obtaining all necessary flight permits, notifying the appropriate parties, so that means like the FAA, landowners, we have to notify the nearby airports, the training people. One of our sites is pretty frequently very low flying helicopters go through there a lot because the training school is right across the river. So yeah, we let them know. They can make a little lesson plan about what to do about that. So after we notify everybody, we make the mission in our software mission called Mission Planner. We make the mission to basically where we're going to fly, the kinds of lines we're going to do, the angle we're going to fly at, the time we're going to fly, that kind of thing. We decide on ground control point locations and get those deployed, and do our pre-flight check. So that means like make sure everything is charged, make sure the drone is in good working order, do any maintenance that's required, that kind of thing. And then we get to the flight portion. So this pre-flight check, we do another one. We want to make sure that everything is connected, everything is plugged in, everything is turned on. This drone is not at all idiot-proof, so there was a time we flew a site called Campbell's Slough without turning our LiDAR sensor on, so we had to fly it again. Luckily it was a small site, and it took another 45 minutes, and it wasn't tidal, so it was totally fine, but just kind of annoying. So you fly the entire site for LiDAR and then we land it, transfer all the data, back it up. Steigerwald, for example, about 1,100 acres was nearly 4 terabytes of data. Wadiski at 250 acres was about 800 gigabytes. And overall, last summer we collected 12 terabytes of raw data, and we have about 8 terabytes of processed stuff so far. And with another probably like 6 to go. After we do the thermal, or the LiDAR and multi-spec, we fly targeted locations for thermal. So that means, we'll look at Gibbons Creek channel emptying into the Columbia and how the thermals of that are affecting things. So we'll look for like cold water refuges and seeps and that kind of thing. We do the entire flight in Mission Planner and Ardu Pilot. So after we fly and we get back, we process everything. So number 1 is LiDAR. We process this in LP360 and rasterize it in Arc Pro. So basically we create a classified point cloud and then export that. And then with that we have a DEM and a canopy model, and it's like a super dense point cloud, so we can look at it, do tree counts, look for beaver dams, do cross sections, elevations. And you can do segmentation analyses to see how many trees you have, that kind of thing. And like see how thick the trees are. It's pretty cool. Next, you can do multispectral. So we do this in Pix4D and composite it within Arc Pro. So the number one thing we make is a pretty orthomosaic. We also do indices and reflectives maps. So we create thermal maps, vegetation indices, model the vegetation, look at the vegetation health, pretty pictures. We do like unvegetated to vegetated ratios, that kind of thing. Finally, we have the thermal sensor. So we process everything in Thermolab for that, which is the proprietary software that's required. And we can create thermal videos, images, a thermal map if we want to, and just kind of a lot of pretty pictures. We can look for like count the white-tailed deer or something if we wanted to, or the pelicans or whatever. And lastly, we have a lot of reports that we can produce from this. So we can do like digital elevation models, vegetation maps, thermal maps, planting survival maps, etc. And that's a lot of what this discussion later is going to be about. So let's talk about acquisition, first of all. So number one, ground control points. This is the most critical component where if you get it wrong, you have to refly. So this one on the left is a temporary ground control point. It's about 14 inches across. This thing will dissolve after one tidal cycle. And then all that will be left are these little like toothpicks, and those will dissolve after about a week. And they're gone. It's cool. So this one is a LiDAR ground control point. It's about 4 feet from here to here. You can't quite see, but it's 4 feet across. These little discs are about 5 inches, 4 or 5 inches, and they show up like super bright white in the LiDAR imagery, so we can pretty easily ground the LiDAR cloud. So, moving on, ground control points in more detail. We try to do about 5% or 1 every 30 acres, whichever is greater. And then obviously safety is a concern for some of these sites. So on the left, this is Steigerwald. It's a very safe site to walk through, so every single one of these like crosses is a ground control point we deployed in, I think, 2023. This is a lake right here. No, this is the fan, sorry. This is like inaccessible. It's terrible. So we just put them around it. I think we put one inside too, but it was bad. Anyways, this is Wetland on the right. This is a tidal wetland with some terrifying mud flats. And channels really. So down here in this section, this was too unsafe to get to, so we skipped it and did not ground control point it. Up here is also particularly sketchy and very hard to access, so we skipped that as well. So moving on, how exactly does a drone flight work? This is pretty ubiquitous, what everybody does. So number one, we launch and get positioned for the flight. Once we're in position, we do a pass across. This is about 12.7 meters wide, and then we go to the next. We've moved over 12.7 feet and are doing another pass down, getting around an 80% overlap. And then we do it again, pass number 3. And then you do that over and over and over and over, and eventually the entire site is mapped. So this was 112 passes for Wetland this time. Yeah, it took about 2.5 hours, maybe 3. To get all of this done. And in hindsight, we should have started about a half hour earlier because the tide was starting to come in down here. So we lost some resolution down there, unfortunately, but it's okay. So, LiDAR. Let's chat about that now. So number one, how does it work? We have a TrueView 515B LiDAR sensor. It has 2 RGB cameras, so here and here, and then a laser scanner. This laser scanner is infrared. They also make green LiDAR, but infrared is for vegetation penetration, green is for water penetration. It is GNSS enabled, so we have about 5mm precision, 20mm accuracy. And then about 3cm vertical accuracy overall and 2.5cm horizontal. And we have about an 80-meter max range for it before it loses too much energy to like reflect back well. So, how exactly do we collect our LiDAR data? So number one, obviously we continue to do our little back and forthing thing. So in this, obviously we have a little wetland. This is my Microsoft Paint skill, it's coming in handy. So here is, the black is our land surface, blue is a little channel. This is a tree, this is a tree with a lot of vegetation. So, as you fly back and forth, we have constant returns. So this first return is the canopy top, or it's like a water droplet like way up here, but we throw that up. This is the first real return. That's the canopy top. The second return, we hit every single canopy layer as we go down. Our last return is the ground. There's nothing else that's going to be past that. Sometimes it's a solid object, like a building, or a car, or a log or something, but it's always the last one. If this were angled slightly more, we'd see the tree as our last one. Sometimes it goes through the trees. It really depends, but yeah, we can clean that up as we process it. So as we move forward some more, we hit the water. So we get about 10 returns from the water surface usually, and they're like super tightly clumped. But we don't get anything below the water with our infrared LiDAR. If we had green LiDAR, we'd get this return as well, but we'd lose some other returns. But yeah. If the vegetation is too thick, we don't get a return at all from the ground. Like it fizzles out like up here or something. Right? So this is like a super thick blackberry bramble or super thick trees. We do still get some returns because there are angles where we can see, but there might be a little like hole right here that we have to fill in with everything around it. So, here's some pretty pictures, right? This top is the classified, or this is the colorized point cloud. This middle one is a colorized by elevation, so you can really see the channel forming in through here and what, yeah, just the channel. Down here is the classified point cloud. So the orange is ground, this dark green is low vegetation, and this light green is mid and high vegetation. So you can really see all of this little light green stuff right through here. You can't really see it on that RGB image, and that is because it's like 2 inches tall. And so we can pick it up with the LiDAR, but it's really hard to see in most imagery. So I would be remiss if we didn't talk about our accuracy and precision. So we have about 3 centimeter precision across the wetland and 5 centimeter vertical accuracy across the wetland, as compared via a TopCon R2K, like a network R2K system. We have about 1,500 points per square meter, or a ground sampling distance of 2 centimeters. This entire project was about like 900 million points or something, or 1.1 billion, I can't remember, but it was some insane number like that. Standard USGS LiDAR is quality level 1, so that means 6 centimeter precision, 10 centimeter accuracy, and about 8 points per square meter. And it's really designed for roads and hard surfaces. So right along here, you can see the road in this dark green. That is our LiDAR's kind of precision levels. You can see it's really good through most of it. There are places with the light green. That means we have about 3 centimeter precision instead of 1 centimeter precision. Whereas like this yellowy color up here, that means we are more than 4. So it drops a little bit, but we're not really interested in the stuff up here. We're really only interested in stuff down here. There are a few spots, like right up here, there's a lot of blackberry, so that drops it. Here there's actually a cell phone tower, or a power tower thing. Anyways, moving on. So, channel development. Let's track that. So on the left, we have 2010 LiDAR from the U.S. Army Corps of Engineers from pre-construction. So you can see these 3 different channels right there. On the right, we have the current LiDAR overlaid with the construction plans, basically. So those blue are the channels they constructed, or enhanced, or whatever. And then these orange things are the mounds. So, we are here, looking this way. So we're looking here and looking this way. This is this tower, and that's right there. But you can really see the channel development, like right through here. We have a bunch of new channels forming. Over here we have new channels forming. And there's just a bunch of like pretty fabulous enhancements. Here's the north half side of the site. So again, you can really see these enhancements like right through here. And over here. This one is already there, but yeah, it's pretty incredible what we can do. I'm gonna focus on this little region down here for this next slide and talk about the channel cross section. So this is a cross section that we didn't really care about, but it's pretty incredible. We're moving upstream at about 1 meter per frame. This is a dry channel at the time, and like This LiDAR stuff really just augments and enhances our manually collected cross sections. We still do have to do manual cross sections at times when there is water, but you know, that's okay. So you can really see it steepen out there and mush open there, and it's pretty cool stuff. I'm gonna arrange to the next slide, but yeah, this is a beaver dam from MCNA, I believe. So again, this is that same kind of channel profile thing, except we're longitudinal, so we're going directly upstream. So this is the downstream side, beaver dam, and then the upstream side. This is kind of bumpy because it's more like fast moving right there, so there's a little bit more noise in the data. This is the beaver dam itself, and then this is the upstream water surface where it's kind of a lake. And it, you know, really pops if you know what you're looking for. This is another beaver dam. So this is Stargarwell. There's a little mound right here. If you ever go out there, you can see it, and it's pretty incredible. This is what it looks like in the LiDAR. So this is a tinned surface of the water around it. This is the beaver dam. It's very large. It's like 1.3 meters tall and 7 meters wide. It's huge. So let's talk about trees now, the bane of everybody doing LiDAR. So even areas with very thick canopies can still create pretty accurate ground EMs. So in conditions like this, where we have full leaf-on conditions, it does reduce the quality of the LiDAR from QL0 to about QL1. Leaf-off conditions continue to create QL0. So if ideally we fly this in winter and in summer. And with this, we can do tree counts, carbon stocks, speciation, etc. So this is an actual image of what the point cloud looks like. So this middle is the colorized point cloud, and this left is the ground surface, and the right is the elevation. So specifically, I want to draw your attention in the ground. You can see all of these like little larger triangles. This is where it was too thick to really see the ground. But it still does make a very accurate ground surface. The right is how we count the trees, basically. So each slope change is considered one tree, or one crown top. So here's a crown top, here's another crown top, so we can go through and count it, basically, with an algorithm. I'm not doing that manually. Yeah, so here's another example. This is Steigerwald, and one of the planting locations that they did. So we can really evaluate the effectiveness of the plantings at these restoration sites for willows and that kind of thing. So this point cloud really provides information on density, count, height, mean coverage, survival ratios, growth rates, that kind of thing. You can see they might need to do some infill planting right through here because it looks dead and there's missing trees. Stuff like over here, these just look like stunted growth. Are they getting enough water? I don't know. You know, that kind of thing. But yeah, it's pretty cool. And lastly, we can really do as-builts and check those to make sure they've constructed everything correctly and like determine how it's changing over time. So this was fully vegetated. You can see right here there were some willow plantings, and down here there was some more willow plantings or something. But you know, you can see that little mound right there. And yeah, I mean, you can just, it's a perfect match. It's very cool. So now we're going to discuss some multispectral stuff. Number one, what is multispectral? Multispectral is a way of separating the light bands into different bands. It kind of expands out. So as a human, we can see red, green, and blue. With the multispectral, we add red edge and NIR. So they're just different wavelengths of light. We are flying 5-band multispectral, so red, green, blue, red edge, and NIR, at about 3.2 megapixels per band. The DJI is about 2.2 megapixels per band, for reference. We also have our thermal camera right here, and that is a pretty low resolution, actually, unfortunately, but it's pretty amazing for what it is. Like, they don't make high-resolution thermal cameras. This is one of them. That is very high resolution, actually. We also have an ultra-high-resolution panchromatic sensor, so that, yeah. It is RTK enabled, so we inject an RTK signal with PPK, I believe, via an MLID reach RTK. To fly it, we use Mission Planner, Pix4D to process, and Arc Pro to kind of display it. At Steigerwald, we collected like 140,000 pictures. It's like ridiculous. Every time it takes a single picture, it takes 7 pictures. So, and it takes those 7 pictures like every second and a half or something. So I want to compare explicitly the difference of level of effort between the DJI drone and the Harris drone. So this is our 2022 flight, I believe. We have 31 ground control points across the site, where we record an RTK point, take photo points, record the dominant species. We also have some vegetation grids, so those are just detailed species data, basically. The DJI drone, we flew at 300 feet, 80% for inside laps, and flew it over 2 days. So that was pretty slow. It also took us 2 days to the ground control point, so we were here for a week, and timings are on. But so PIX 480 processing options. Yeah, we ended up having 3.73 ground sampling distance, and then we did all the things. So next slide. The Wadowski field survey work with the Harris drone. There's a typo there. We had 15 ground control point locations. As mentioned previously, we skipped this section because of how challenging it was to get to, as well as this section up here. We flew at 245 feet, and it took about 3 hours to fly it. So, we create individual spectral bands that are combined to form that RGB map, so red, green, and blue. I don't know why the quality got absolutely mutilated for this, but I apologize for that. We also do LWIR, so long wave infrared map, or thermal infrared. Basically, we can map the thermal signatures of the vegetation community and the water across the entire site and create a map for that. Individual spectral bands are tools to evaluate stuff like water quality, turbidity, chlorophyll A, for example. We can use red edge to do chlorophyll. It's pretty cool, actually. And yeah, I mean, these can go very far and answer many things beyond just vegetation communities. So here are some examples. So we have different vegetation indices displayed here. So we have the normalized difference in vegetation index right here, which most people use. We also have the NDRE, or red edge, and we have the enhanced vegetation index. So NDVI is really mostly used for things at peak biomass. It is a measure of how much photosynthesis it's doing, pretty much. Different plants do different amounts of photosynthesis. It can do stuff that's not at peak growth, so like when dieback begins to happen, they really start popping here. So in the EVI, for example, this top half seems to be having, it's farther along in the growing season, so it is starting to die back in the north. In the south, it's still super happy and active. You can also see it's slightly more stressed up here and less stressed down here. So with this, we can really identify invasive species. We can expand our flight season, vegetation modeling season, and it's just pretty incredible what we can do with it. So ultimately, we're integrating all of these products with machine learning and AI. You know, the buzzwords, right? So we're using a random forest machine learning model, and we're trying to develop a CNN to just make our life easier and just do this faster and better. So this image tour, right, is the classified model. So you can see some, I think these are Phragmites or cattail, I'm not really sure. And then we have some bulrush down here. This purple is blackberry. Lots of fun stuff. We can combine this with our canopy model and develop kind of a biomass analysis. We have an eddy covariance flux tower right here that's capturing this entire swath, so you can map the emissions that's getting picked up from that flux tower onto the wetland, determine what percent the methane is coming from reed canary grass versus cattail versus bulrush, etc. So moving on into thermal. So we have thermal imaging and restoration, like it's critical. The thermal camera we have is the Orexhole Wireless Enterprise, right here. So in it we have a 30x optical zoom, 16 megapixel camera, thermal camera, and a laser rangefinder. It has an accuracy of about 2 centimeters, plus or minus. The accuracy plummets after about 1.5 kilometers, and it's particularly useful for assessing water temperature patterns, identifying areas of erosion and sedimentation issues just with the picture taking, and we can assess vegetation health. Yeah, so moving on. So this is surface temperatures. I want to be very clear that they're not necessarily under, we can't see under the water. We only are seeing the surface. So when it's sunny, it's going to look hotter. When it's not sunny, it's going to look colder, where it might be the same temperature if you move 2 centimeters into the water column. In this case, it was not sunny. So you can see that there's some popping right through here along the levees. So for whatever reason, water is likely being held inside of here. You can also see that it's low quality and everything is like on an angle. The gimbal came broken and it's finally replaced now, so doing good. This is Franz Lake. So you can see this is Mainstem, Colombia. It's about 4 degrees Celsius, and this is like February. It was very cold this day. This is Franz Lake itself, so you can see it's slightly warmer. This is where Indian Mary Creek comes in. You can see it kind of flows mostly this way, actually. And yeah, you can just really see that temperature signal pop in. So ultimately, reporting and research applications, like what are we actually interested in? So number one, you know, we can come in pre-restoration, right? We can combine it with hydraulic models and, you know, plug in like what the site is actually doing right now before restoration and assist in the planning and design and adaptive management of that site. So for example, if we are expecting, you know, 2 centimeters of sea level rise per year, we can plan around that and just do a lot of cool things to accommodate for that. Just kind of how we plant the site, for example. Like, we're not, yeah, it's pretty cool if we need to plant the site, and we can ultimately predict what species are there, kind of based on that elevation. So the biggest thing we're trying to do is plants, because we're plant people. So in the past, we've done like giant vegetation transects where we do about 1 meter of data, and then like every 5 meters and go along the transect for 100 meters. We collect about, you know, 0.02 acres, right? With LiDAR, or with the drone, with a drone, really, we can expand that to like 200, 1,000 acres, right? Infinitely expand within reason. And we can track site-wide change over time and predict shifts from like sea level rise, climate change, restoration, targeted management, that kind of thing. I do want to explicitly point out that we are going to be losing the understory, so we cannot really see that. And some of these sites are so diverse, we also really can't see like every individual blade of grass, for example. We can see like, you know, communities. If it's less than about an inch, we can't see it in the imagery directly. So, ultimately, we plan to include channel tracking and overall topographic development and evaluate above ground biomass stocks. Those are the 2 biggest things we're doing right now. We're also doing a bunch of thermal sensing. Yeah, so I mean, the sky's the limit with what we can do, really. So we are refining our protocols for thermal sensing now that we have our gimbal that is hopefully fixed. We've not used it yet, but it should be good. We're going to utilize LiDAR to continue to evaluate sediment dynamics and topographic changes at different restoration sites and ecosystem monitoring sites as well. We're currently developing a predictive model for vegetation development at restoration sites using these machine learning algorithms, and we're ultimately trying to kind of migrate to an AI model with that deep learning CNN thing we talked about earlier. We're developing a site-wide biomass and ecosystem health analysis, and we're working closely with sponsors to develop sampling plans that align closely with the restoration goals. For example, if people don't care about the plants, we don't have to do the plants, right? We can just do temperature or whatever. Ultimately, we'd like to thank all of our research partners, specifically Ryan and Lasmar, for being more than willing to ground control point with us. It's pretty terrible and dangerous, but we have a good time with it. We'd like to thank the Cowlitz Indian tribe for letting us have access to some of their sites. We'd like to thank CLT for, again, letting us have access to their sites. We'd like to thank Bonneville Power for funding most of this work. And, yeah, really just want to thank all of our partners for all of the hard work you guys do. So thank you, and have a wonderful day.